So, we will discuss about the carrier concentration in semiconductor and Fermi level of that semiconductor, right. I have discussed already that there are two type of semiconductor. One is intrinsic semiconductor. This say we have band so this is valence band and this is conduction band. This valence band. So, this energy scale, this side it is 0 and this side goes to infinity, right. So, this edge of this lower edge of this conduction band, this energy is defined by say E c, and this valence band edge, top edge, this energy is E v. And Fermi level or some we can tell this here for intrinsic case. So, this so this energy is say E I. Okay. So, for intrinsic semiconductor, so this Fermi level I am defining here this by E I. So, I will show that E I will be equal to E f. So, in this case this is the band diagram and this energy of this E c, E v and E I, and another is this gap, this energy gap. This we write is this basically E g energy gap between the conduction band and valence band. So, E g equal to E c minus E f, sorry, right. So, when for second type is extrinsic semiconductor, and in this case the two types, either N type or P type. So, N type, again this band diagram if I draw, So, in this case, so this again we see this is EV, okay. Now, this for n type pentavalent impurity we have doped. So, this so that is called donor. It can donate electron in the system, it can donate electron to the conduction band, and it is assumed that this donor energy level is close to the conduction band. Generally it's this difference is very small, say 0.01 to 0.03 electron volt. It depends on semiconductor and type of dopant, of course. So, this energy level of this donor, it's we can write ED, right, and this Fermi level. So, now, so this donor level is having electron, this atom is having 5 electrons. So, 4 are they have formed bond with the silicon, 4 silicon, and 1 extra is there. So, this 1 extra electron, it is in this level. So, this electron from this donor atom, it can go to the conduction band, okay. So, for that this donor needs some energy. So, that energy is difference is EC minus ED. Now, this Fermi level, in this case it is considered that it is in between these two, that ED and EC. So, his is considered EF, okay. And for P type semiconductor, so we have similar band diagram. Right. So, again this is EC, EV. So, this P type trivalent atom is used for doping, and it has 3 electron. So, to satisfy 4 silicon, nearest neighbor 4 silicon. So, we need 4 electrons. So, 1 electron is missing, basically 1 electron is missing. So, that means this atom which we use to dope the semiconductor, intrinsic semiconductor. So, that it is trivalent and 1 electron is shortage. So, it can accept, it is ready to accept 1 electron. So, that is why it is called acceptor, and it can accept from where? From valence band. It can accept electron is available in valence band. So, it can accept electron from the valence band. So, this acceptor level it is close to the valence band. So, this energy level is there. So, it can accept electron from the valence band. So, this again this energy difference EV and EA, this is few very small electron volt, is 0.01 to 0.03 in that range, okay. So, here this Fermi level again. So, now electron is accepting from valence band. So, is exchange between this EA and EV. So, Fermi level it is expected between these two energy level. So, this is EF. Okay. So, let me make it solid. Let me make it solid. So, this is ED and okay, and EI whatever here given. So, that is it's basically it will coincide to the Fermi level. So, EI and EF is at same place, okay, because here electron is getting exchange between this conduction band and valence band. So, EF also expected at the it is a middle, okay, and it will coincide to this EI. Okay. So, EI and EF it will coincide. So, here, so this is the picture of semiconductor, band diagram of the semiconductor. So, here just I assume, okay. So, this is the type of arrangement of this energy levels, but that we can find out. For that we have to calculate carrier concentration of semiconductor. So, if I do that, so let me tell you that I think I will. So, I will just so how we can calculate carrier concentration. So, carrier concentration means, as I mentioned, that density of function dn by dE, right. We write generally density of function. Okay. So, we remember for free electron we have calculated density of functions. What was that? So, V by 2 pi square already I have derived this one, V by 2 pi square 2 m by h cos square to the power 3 by 2, and it is basically proportional to the square root of energy. I think that was the expression for density of function. Yes, okay. And Fourier function that Fermi-Dirac statistics. So, this is the density of states. Now, each state will have one electron, because density of states we have. So, in this formula we have considered that this one level can take 2 electron, spin up and spin down. Okay. So, that means it has degeneracy. So, now if we multiply with 2, then 2 into that number of orbitals. So, it will you can consider double orbital, then we have to take this 1 electron per state. Okay. So, that is the 1 electron per state. So, that we have considered when we derive this one. Now, so this we have to adopt for our system. So, here this this is any energy, right. So, here we want to consider that in conduction band, what is the density of states, right. So, conduction band, so it is above EC. So, any energy if I consider here, so that is E. So, actually E means this E and minus E c will give this. Okay. So, here we have to modify this one, basically we want to find out the density of states, this energy range. Okay. And now number of electrons. So, dN in the energy range E to E plus dE. So, that will be the okay. So, dN is this. So, n will be one has to integrate this one, right, over d. What is the range? What is the integration range? So, it will be E c to infinity, E c to infinity, right. So, E c to infinity density of states, and now we remember this density of states is basically for t equal to 0, t equal to 0. Now, we have to for finite temperature to calculate density of states for finite temperature. So, we have to multiply with the Fermi distribution function F e, right. What is F e? F e is, you remember F e is F e is 1 by 1 plus exponential E minus E f by k t, right, E minus E f by k t. So, it is not visible. So, I should write slightly. So, this F e I should write somewhere here. So, then I can keep it. So, F e basically 1 by 1 plus e to the power or exponential E minus E f by k t. Right. So, so that is the case. Now, in our case you see this if I consider that, assume that k t, that E minus E f is very very greater than k t. So, temperature is such that this you cannot see probably. So, if I assume that E minus E f is very very greater than k t. Okay. If it is equal or less than k t, so all electron will easily go to the conduction band, right. But if it is temperature is such that this E minus E f is very very less than, very greater than k t. Okay. So, that means this term is very very high. So, e to the power is very high term. So, it is quite high term compared to the, this value will be quite high compared to the 1. So, I can neglect 1, I will keep it, I can neglect 1. So, this 1 by this, that means exponential. So, this Fe will be 1 by this, means exponential. So, it will go up minus of this. So, minus, so I can just write minus, I include here. So, Ef minus E, right, by kT, right. So, for our system, so we adopt this Fe. So, now if it is for, we are calculating this concentration of electron. So, here EC to this, if I want to calculate concentration of hole, so concentration of hole, so this integration will be, this integration for P, this integration will be, so from EV, from 0 to EV, so 0 to EV, right, in case of hole. So, in valence band, what is the number of holes or density of states. Okay. So, in that case, I will put here E, electron density, I will put here E. So, this is for E, right. So, density of states, here we have written whatever this one, E minus EC. So, that is for E. Okay. So, similarly for hole dH, if I write hole dH, if I write dH as a function of E, then what it will be? So, here this density of states per unit energy, density of states means states per unit energy. Now, if I divide by V, volume of this material, so it will be density of states for unit volume. Okay. So, we are, so this dN or N, it is basically for per unit volume. Okay. Density of states or density of electron, because in each state one electron. So, density of electron is N. So, per unit basically volume. Okay. So, VA I make it 1. So, DH, so this F. So, for that this appropriate one. So, this is there, here this our it was e to the power half, right. So, in this case, so this here this between these two EF and this EV. Okay. So, that energy is here, I want to find out the density of states here. So, energy is here. So, with respect to the Fermi level, so then E minus EC. So, now I have to write that one EF E minus EV minus E. Okay. In this case, I have to write EV minus E. Okay. So, E is here, the EV minus E. Okay. So, E value is from origin, this is whatever E value from origin, this is the EV value. So, EV minus E, so this will be this range. So, within this range I want to find out the, so EV minus E. So, in case of DH, so this will be EV minus E, EV minus E, okay, to the power half. So, this will be for DH. It will be for DH, it will be for DH, okay. This will be for DH. Density of states of hole in valence band. So, in that case we have to use EV, okay. So, and this this Fermi distribution, it will be FH G equal to. So, in this case also we consider that this term is very greater than this k T. Okay. So, this term is higher and you will get again this similar type of things here. So, E f minus E e. So, in this case also you will get no. Yeah, I think that way one can consider, or generally what we do 1 minus, generally what we do, because density of this electron distribution, this F e is maximum value is 1, right. So, for hole it will be 1 minus F e whatever for electron. So, this 1 minus this. Okay. So, from Fermi level, if I draw here, yes, this is the energy, this is the energy, this is the energy. Okay. Now, this is the Fermi distribution, this is the Fermi distribution, this side. So, this is F e. Okay. What was that for temperature at T equal to 0? So, this it was like this. So, up to Fermi level, it was 1, and then 0. When temperature is not T equal to 0, then what happens? So, okay. So, from here whatever electron, so it goes above Fermi level. So, its probability decreases, its probability increases. So, that is why whatever probability decreases is increases here. So, total probability will be 1. So, that is why it is 1 minus F e. Okay. So, from here, so just it is 1 minus this F e got, or you can get from here also 1 minus this. So, 1 minus this means, so it will be exponential, yes. So, not F e, just I will start from here. So, it will be F e. So, it is 1 by 1 plus exponential this term, right, this term. So, this it will give you e to the power exponential this term divided by 1 plus exponential this term, right. So, if you divide it by this, the 1 by exponential plus 1 by exponential, whatever this sign is there, it will just reverse E f minus E, it will be E f minus E. Okay. So, E f minus E plus 1 by, okay. So, E f minus E. So, in that case this term is very greater than 1. So, that is why you can neglect 1 here. So, this whatever you will get. So, if you take off, so again minus sign. So, it will come in original form this way. So, it just reverse whatever exponential here, it will just reverse of it. Okay. So, it will come exponential E minus E f by k t. Hopefully, I have done correctly, but this is the way one has to do. Okay. So, one can integration, that limit I have given, so one can do. Okay. So, if you can do one, so other one also you can do, but these are the things here. So, just I want to calculate for this n. So, let me just forget this part. So, in this case, so this is the density of, this is the F e I have to use, F e, this is the term, and dE is this one. So, n equal to what I will get? So, this you take out from this integration 1 by 2 pi square 2m by h cross square to the power 3 by 2, okay, and you will get here integration EC to infinity, and then I am getting here E minus EF to the power half E minus EC to the power half, and what I am getting here exponential EF minus E by KT, okay, and DE. So, you will have this term DE, right. So, DE, okay. With respect to DE, one has to integrate, and then so this integration one can find out. So, what I will do here, this term, so exponential EF by KT I can take out, and then actually here I want to set E minus EC. So, this I can add plus EC minus EC, okay, here. So, I want to keep it this E minus EC. So, if I take minus common, E, this plus EC will go, minus EC, that will be there, and EF minus EC by KT, this will be another term. So, I can take out here, multiplied here exponential E minus EC then that minus sign is there, E minus EC, sorry. So, EF minus EC, this term by KT, this term I will take out, and what it will be there? It will be there EF minus EC I have taken out. So, EC minus E it will be here, EC minus E will be here, okay. So, if I can take minus sign, and then it will be E minus EC. So, minus, so this I can write minus E minus EC, okay. So, if you take this E minus EC equal to x, E minus EC equal to x, okay. So, then dE equal to dx, okay. No, so I think I need space. So, basically here if you take E minus EC by KT equal to x, so dE equal to KT dx. So, from here you will get dE equal to KT dx, right, KT dx. So, KT term will come here, and this KT I can take out. So, this x, this dE basically I can replace by KT dx, KT I can take out, okay, and this then x to the power half, and e to the power minus x dx. Okay. So, this will be the integration, and this integration limit will be here when E equal to EC. So, here E equal to EC, then x will be 0, right. So, integration will be 0 to this, 0 to infinity. So, this is the standard integral, and this its integration value. I think this 2 by pi, square root of 2 by pi, integration is square root of pi by 4, square root of pi by 4, and yes. So, this integration it will give you pi by 4, this is the standard integral, it will give you pi by 4 to the power half. So, actually you are getting this after this integration. So, this okay. So, this term this will be there kt and this variable. So, overall you will get so I will get n equal to just if you do so 2 I will get 2 me for electron. So, this basically effective mass kbt. Okay. So, somewhere I am writing k or kb the same, right. So, kbt divided by 2 pi h cross square to the power 3 by 2 exponential ef minus ec exponential ef minus ec by kt, okay, by kt. Okay. So, this you will get after this calculation, you will get this, and similarly if you calculate for P, you will get mH whole effective mass kbt by 2 pi h cross square to the 3 by 2 exponential this just EV minus EF by KT. Okay. So, here if you take product of this NP, what you will get? You will get 4 and this you will get KBT by 2 pi h cross square to the power 3 by 2. So, this 3 and MH star. So, this you will get 3 by 2 and this exponential you will get. So, EF will go. So, you will get EV minus EC exponential EV minus EC. So, this is so this will give you EG minus EG. So, EC minus EV is EG. So, EV minus EG minus EG. So, it is basically you will get minus EG by KT. Okay. Now, this product if you look at it, so you see this is independent of Fermi energy, no. This is independent of Fermi energy. Now, I have shown you that this Fermi energy, this position depends on the whether it is intrinsic semiconductor, whether it is p type semiconductor, whether it is n type semiconductor. Depending on that, this Fermi energy is shifted, but EG is always same. So, this product So, it is so this in this calculation I have not mentioned that it is for intrinsic semiconductor. So, it is in general this product is always constant for a particular temperature, and this is called the is called this law of mass action, law of mass action, law of mass action. So, this product is always here. So, if it is for intrinsic semiconductor, so this product is intrinsic semiconductor Ni. So, this for hole and for this other. So, this electron. So, Ni square intrinsic semiconductor, if it is constantly Ni. So, Ni square equal to basically Np equal to this. Okay. So, this is valid for all semiconductor, because it is independent of Fermi energy, and this is called law of mass action. Okay. So, this very important finding. So, I will continue in next class. So, I will stop here. Thank you for your kind attention.